So we've developed some recursive updates for our autocorrelation matrix Rx and our cross correlation RDX, and then we developed a recursive update for Rx inverse, which we labeled PN, and that's shown boxed here in green, but it had this G factor. So then we came up with an equation for the G factor. Actually, we had that right up above. And we thought, well, is there a recursive way to get at that? And we found that there was. But some of you may have noticed that we have a problem. The problem is that G appears in the equation for P, and P appears in the equation for G. So it turns out that this simple form, while instructive perhaps, isn't going to be useful in practice. We're going to have to revert back to the other, but we'll do that in due course as we get to our weight update. So ultimately, we want an adaptive filter where we filter the input with a weight equation x, and then we will we'll have our output that's the estimate of RDX, or the estimate, I'm sorry, of our target D of n, and then we'll use that to update our weights for the next time. So to start this all out, we will use the normal equation to find the ideal weight, set of weights at a given time. So this normal equation is based on our estimates, but that's what we have to work with, so that's just fine. And we can rewrite this, of course, in terms of our Pn now. And remember, our Rdx of n is our recursively updated estimate. It's not the actual expected value, it's rather a weighted time average value that we're looking for. Well, in the spirit of everything that we've done so far, we're going to try to find a recursive update for W the same way we did with our other adaptive filters, where W is now subject to some update based on its previous value. To do this, let's rewrite this using our recursive update for RDX and see where that takes us. Now obviously, if you'd been the first to discover this, you wouldn't know exactly the path to take. You would have tried various things and eventually gotten there, but we happen to now know this well-worn path, and that this is a very good way of getting where we want to be. We would get lambda Pn RDX n minus 1 plus Dn, which is a scalar, so we can pull it out front, Pn x of n. So as we've seen before, it's going to get worse before it gets better. We can now substitute in our what we know about lambda Pn. As we looked previously, lambda Pn from this equation in the middle here is going to be equal to I minus G of n x transpose n P of n minus 1. So as we come up with our weight update, we're going to be following this general procedure of trying to get everything in terms of something at the previous time whenever possible, except of course our dn and our xn, which have just been given to us. Okay, so let's make clear everything we've done so far. This right here, as we just mentioned came from the expansion of lambda times p of n. That was part of that recursion. This was Pn x of n. That's what we found last time, and what I just mentioned is our useless recursive equation, because we have Pn as a function of g and g as a function of p, but it's still very useful for simplifying this setup right here. Okay, maybe simplifying isn't the right word, because we took something, I guess, here that was a little more complicated, made it simple, and here we expanded things out. Okay, what comes next? Well, we can note that we've seen this expression before. P times r dx. P times r dx we found was just equal to our weight. But in this case, it's at time n minus 1. So we'll have overlapping things here. This is equal to w n minus 1. Okay, we can put all this together. Let's see, what's that going to give us? We'll have the easy part. Wn stays there on the left side. That works. And now we have Wn times I is going to give us, or rather Wn minus 1 will give us that out front. Then we have Wn minus 1 times g times and x transpose. And we also have a g and a d over there to the right. So let's combine those two equations, giving us a g out front, and then our d of n, and then minus, we had our x transpose times Wn minus 1. We're going to flip things around just a little bit. We could go either way. And right now we're dealing with a real situation, so it doesn't really matter. Because W transpose n, or W transpose x or x transpose W are both scalars, or results in a scalar in both cases, we can swap the order. Of those two quantities, as long as we keep track of the transposes. And there we are. We're going to keep working on this, but first let's discuss what exactly this means. We're used to seeing d of n minus w transpose times x. We've seen that before. In this particular case, we're using n minus 1 times x of n, and we're going to call this the a priori error. This is the error we would experience if we did not update the weights. Well, if we're distinguishing this, as you might imagine, we will care about the error that comes after. This is not the error that we defined in our previous page or lecture. There we defined the error as EI is equal to DI minus WN, so the current weights, times XI, and where I range from 0 to n. So we're not quite there yet, but we're going to give this a name then that's something different so we don't confuse them. We'll call this error alpha sub n. Okay, let's put together what we have so far. We have our G, and in order to not have a recursive definition, we're going to have to go back to our slightly more complicated version. Like so. And we have our P update. It's equal to 1 over lambda times I minus, and now we can use the G that we have just calculated. Multiplying our current signal input and then our previous weight vector. Then we calculate our a priori error as d of n minus W transpose using our previous version of the weights times our current input. And then finally, we can update the weights using a recursion as we've done in the past. And now we're using our alpha n times our vector g of n. Finally, we have our filter output. That is d hat of n is going to be equal to W transpose n times x of n. So one of the differences you're seeing here is that we actually calculated an error already with our W transpose n minus 1 times x of n. Then we did the weight update, and then we calculated our filter output. So when we're looking at LMS, our filter output was actually the W transpose n minus 1 x of n. So we have a different filter output in this respect. Well, there is one other simplification that we can do to kind of reduce the number of calculations that we have to perform. And while this version that you're seeing right here is perfectly valid, we can reduce the number of calculations by noticing that both G and P contain the same term, P n minus 1 x of n. And so if we define, if we pre-calculate that, essentially it makes things a little bit simpler. So we will define z of n is equal to P n minus 1 times x of n, giving us this a little bit simpler version down here, where we'll have z of n is equal to P n minus 1 xn. Now G looks a little bit better. We actually have fewer computations to perform. I'm going to write this way just to illustrate that what's on the bottom is just a scalar, because we now have the inner product of z with x, and that all multiplies z. Well, that's looking a little bit better. And then our weight update is the same, and our p update is going to be involving the z. Okay, you notice that I folded in the alpha instead of calculating it separately. I just put the a priori error back in there, partially to just save room as I'm writing and near the end of the page, and also because while alpha is going to be important later as we discuss the performance of the filter, for right now, to do the update, there's no need to pull that out as a separate thing. And then finally, our update of p, which is r inverse of x, as you recall, is going to be the same as it was before, but now instead of our p n minus 1 x transpose, we can now put in our z transpose to just simplify things a little bit. So in this is the same filter. It's just formulated differently to do a little bit better on the computation side. I'd like to note a few things. We have a calculation for z. If the length of our signal vector is n, then this is going to be n squared operations. Down here we have x transpose times z, and so that's going to be n operations, and then a sum, an inverse, and then we're going to multiply that by the n values in z, so that's going to be approximately 2n multiplications. On this next one, we have n operations to get w transpose x, and we have n operations to get g times that, and the difference, depending on how you calculate things and what you count, it's on the order of 3n. And then this one is once again a matrix operation, and that's going to give us n squared operations. So we're looking at order n squared on our filter instead of order n for the LMS filters. That can make things really complicated really quickly, especially for a large n. On the other hand, we're going to see later that the performance may be worth it